Hi, today we are going to talk about calculating areas and distances. Well, in high school geometry classes you get to learn about calculating areas of some simple shapes. For example, rectangles, circles, triangles, trapezoids and such. You also learn how to figure out the distance if you have velocity and the time it took for an object to travel through that distance. We are going to look at these topics from a more advanced point of view. Instead of looking at those familiar shapes like triangles and circles and such, we are going to consider some arbitrary shape. We might as well put it in a coordinate system. We are going to consider a function y equal to f of x and some walls, say a wall on the left hand side, call it wall at the point x equal to some number a wall on the right hand side, let's call it x equal to some number b, and a wall right at the bottom, which is the line y equal to 0, the x-axis itself. Question we have is, can we measure the area of this region? Here we have a region limited by the left wall here, right here, bottom is this one, and the top portion is some given function, sine or cosine or x squared or anything else. We want to find out the area of this. You might ask, oh, why do you want to calculate such an area? What is the importance of it? On one hand, from the point of view in geometry, it's crucial to be able to find areas of various shapes. But then in many applications in engineering and sciences, calculating a variety of quantities turns into a problem very similar to calculating areas. For example, very basic issue in engineering, if you have rate of change of something, for example, if you have the velocity of an object, can you figure out from that the distance that has been traveled? Or if you know the rate at which water is leaking out of a dam, can you figure out how much water is still there behind the dam? Or any one of these problems, if you have rate of change of some quantity, can you figure out what is the total change in that quantity? So for example, you might have an electronic equipment, a capacitor or something, and the charges are trickling out of that. It's discharging the electricity that is on it. And you know the rate of change of that quantity, that electricity. Can you figure out total change or total amount of electricity that will exist? Now, how do we approach this problem? So we are going to go back to this area problem and look at that, because it's a lot easier to talk about this than to talk about any of those applications right now. The way to handle problems of this nature is just to reduce it to something we know. And what is it that we know? The simplest thing that we know from high school, simplest area calculation that we have is the area of a rectangle. If I have a rectangle and it has some length and some width, the area of it is simply product of these two numbers. That's a very simple formula. If I am dealing with some curve like this, and I want to find the area that is limited by these lines. First thing I go after is trying to approximate this area. I go ahead and subdivide my region to a bunch of areas that look like a rectangle. So here I go draw some lines, some vertical lines, and by now I have made several strips or several panels that they kind of look like a rectangle. They are not quite, because at the top we don't have a straight side, it's a curved side. In order to relieve our minds, we can go ahead, for example, build our rectangles like this. Then we can go ahead and find the areas of these rectangles. For example, here I might go ahead and find out what this area will be. How do I find that? Well, here's a formula. All I have to do is find out how long the base is, how long this height is, multiply them, and that's going to be area here. And then we can repeat the game for any of these rectangles. Find the area there, and find the area of this one, and find the area of this one, and just add them up. Actually, in some engineering application, they do it exactly like this. They just draw the picture on a graph paper, and then they start calculating these areas. And on a graph paper, you can simply do that by counting the number of squares you see. Well, is there another way of approximating the area? Here we have chosen to subdivide our interval into 4 sub-intervals, and we have constructed these rectangles on the right side of each of these cuts. Now I go ahead and do this thing in a slightly different way. I try to draw something almost the same. Here let's pretend this is the same shape. I do the same subdivision here. This time I can go ahead, make my rectangles on the left hand side. That is, create straight looking rectangles by starting these lines on the left and go like that. So that's going to be one area, that's going to be another one, this is the third one, and this is the fourth one. If we go ahead and find the area of each of these rectangles and add them up, that's going to be an approximation for what we were looking for here. So here's one approximation, here's another approximation. These are very crude looking approximation, but they have the general idea that we are going to be dealing with. Okay, if we go ahead and construct our rectangles on the right hand side, we are going to call this thing approximation from the right hand side, and use the letter R to show that. If we are constructing our rectangles starting from left point of each of these strips, we are going to use the letter L to show this thing. Let's go ahead and do a simple exercise here and calculate the area under some curve by using these simplistic ideas. So approximate area under y is equal to here, x squared over interval from 2 to say 4, using 4 strips or 4 panels, and right endpoint rule. Solving this simple problem doesn't require a picture, but it's going to help us to see what is it that we are actually doing. So here, suppose I have my parabola y equal to x squared. I'm not going to be able to draw to scale here. Suppose this is 0.2 and assume that this is 0.4. So why did I choose 2 and 4? Here I'm told look at it over the interval from 2 to 4. What we really want is the area here. All of this is what we want. Right now we just settle down for an approximation. Our approximation is going to be obtained by using 4 panels. So I go ahead, subdivide the interval from 2 to 4 into 4 pieces. Well, how far is it 2 from 4? This run is 2 units long. If you divide it by 4, each of those is going to be half. So I take 4 at the last point, 2 is the beginning point. I divide that distance by 4, and that's 2 over 4, and that is just 0.5. So it means the next wall I'm going to draw is going to be half a point to the right of this, so that is 2.5. The next wall is going to be at 3. The next wall is going to be at 3.5. Now we said that we want to use the right endpoint rule. What does that mean? It just means that we are going to construct our rectangles starting for this strip number 1. We use the rightmost point at the top to complete our rectangle. So that's our rectangle number 1. Rectangle number 2. This whole thing is rectangle number 1. This is rectangle number 2. This is the rectangle number 3. That's going to be rectangle number 4. Well, how do I find the areas of these things? The first one, first rectangle, well, we need to multiply the base and the height to find the area. The way we set this thing up to make our life easier right now, we chose the bases to be all the same. This base is 0.5, whatever that is, that's your base. How tall is this? Well, that is where your formula comes in. Your formula was y equal to x squared, which means what? Which means if you want to find the height, take your x from here and square it, and you are going to know how high you're going to go. So if your x is 2.5 on the right edge of this rectangle, y is going to be 2.5 squared from this formula, and you plug it in your calculator and you get something like 6.25 and so on. So the area of the first rectangle is going to be the base of it, which is 0.5, times the height of it, which is 2.5 squared, and that is 0.5 times 6.25, and that is something that you obtain on your calculator. Then you repeat this thing. So we go after second rectangle. By now we got the hang of what is it that we are supposed to do. We just go immediately for area. Area, again, here the base is same as before. It's just 0.5. The height now, height is measured at 3. What should I do to 3? Well, I have to square it. To get 9. So 0.5 times 3 squared. And so on it goes. And then we go to the third rectangle. We get area. What is area? Base 0.5. What is the height? Height starts at 3.5, so it's 3.5 squared. How about the other one, the fourth rectangle? Fourth rectangle, again we have area is 0.5. What was the edge on the right hand side? That's at 4. 4 squared is going to give you the height. So 4 squared. Now how about the total? I add up all these areas to each other. So I have 1, 2, and here is the third one, and here is the fourth one. All I have to do is to add them up. Let's be a little bit smart about how we add these things up. You could of course type it on your calculator and add them up, but you want to have an idea as to what's going on. We might as well go ahead and factor this base out because it's common to all this multiplication. So the total is size of the base times, this was the value of x that we plugged in the formula for the function. The formula for the function said square your x's, and then the next one, and then the next one, and here is the last one. Since we got all of this by using the right rule, sometimes they use the notation of R for this. Since we had 4 strips to do this approximation with, they sometimes use R4 for this whole thing. So R4 is going to be 0.5, that was 6.25, and the 9, and that one I guess is 12.25 plus 16. So you go ahead and find out what this one is, and you get some number. So for example, on my calculator it's going to be you have 6 and 12, that makes 19 plus 16, that is going to be 35 plus 9, that is 44, I believe. And when you multiply by 0.5, you get the approximate value 22. So it looks like, let me double check my calculation, this is 25 and what this means is that the approximate value of this area is just 22. Well, you can imagine that you could do the same thing, except that now you might start applying the left rule. Let me go ahead and write that. Do the same problem, but use the left rule. Okay, we don't need to reinvent the wheel all over again here. Left rule is we are going to show it by letter L. We are doing it for 4 strips. The base is the same. Now, do you remember what would be the very first height? How do we get the first height? Let's go back. Well, if you want to use the left rule, let me use the same picture here, getting a bit crowded, but that's fine. This is left rule. Your rectangles are going to be built on the left. This is going to be your first one. So now height is measured starting at 2. At 2 you go up. Next one, this is the second one. The height of the second one is going to be same as the height of the first one in the right rule, and then so on. This is the third one. And here's the fourth one. So how would that go? The very first point on the x-axis is 2, so you have to take 2 and square that. And then the next one will be 2.5, just like here. And the next one is 3, that has to be squared to get you the height. And the last one is 3.5, and then you square that. And then now you get what? L4 is 0.5. This is 4, and 6.25, and 9 plus 12.25. That again is 19 plus 13. That would be 42, I believe. And when you multiply that, you get 21. So here are two answers that we have so far. This was the answer on the right. Using the right rule was 22. Using the left rule, it turned out to be 21. What do you think would be a good idea to do here? In this picture, if you go on the right and you calculate, you're exceeding your area, you're overshooting, overestimating. Left rule is underestimating in this picture. Some other picture, the rules could be different. One is overestimating, one is underestimating. What would you do if you have two approximations and one goes over, one goes under? A reasonable thing to do is just to average them and hope that that's something better. In fact, we do have such a rule. It's called the trapezoid rule, which is just the average of these two. So I just write it briefly. It's going to be called T4. T4 is what you get by averaging these two, R4 plus L4 divided by 2. So 22 and then 21, if you average them, you get 21.5. Are these all the rules that there are? No, really. There are a couple of dozen rules, and thankfully you're going to be spared all the detail of what each rule is going to do. These rules are created to get us the answer to much more accuracy and more efficiency than these simplistic ideas are applied here. But there is one rule that is very effective and easy to apply, and it's called the midpoint rule. I'm going to go talk about that. Midpoint rule starts with the idea that in each of these rectangles or strips that you're using, instead of using either left or the right, create your rectangles starting from the middle. So here is a picture. I quickly draw and explain this. Suppose you have a function like that. You draw your whatever left point you had and right. And suppose we're still doing with the 4 subdivisions. So here is I subdivide by 2, and then here I subdivide again. So I have created 4 strips. Now instead of going to the extreme of starting from left or starting from the right, we just compromise right from the start and do it in the middle. That is, I take this midpoint, go straight up, and create my rectangle here. Here also I create my rectangle here. Here it will be more visible on the tall one. I go all the way up. I start at the midpoint and go straight up, and then I draw my rectangle here, and I attempt to calculate the area of this. Why is this a superior method? Can you pause for a moment and think about why does this method going to give something better than either left or the right? Well, the reason is rather obvious. Here the graph sticks out, and that is what we are not calculating. but by going over here we are including that in the region. We are hoping that these two little triangular looking regions have almost equal areas, and by not including that but including this one, we are letting these two errors cancel each other out. Same on any of these rectangles. So for example, here when I create my rectangles on the midpoint, I am excluding this one but including this one instead, and I am hoping that one is going to compensate for the other one, and that way we get our answer that is much better. Suppose you want to do this thing to the same problem we were doing. Let me draw a separate picture. We had that simple parabola, so let's stick to that. So here is my parabola. We were starting at 2 and ending at 4. And this one obviously was 3 and 2.5, and then 3.5. So this is 3, 2.5, 3.5. What do I need? I need the coordinates of these midpoints, because that's where I'm constructing my rectangles. I need to know what this x is so that I can figure out this y value. Well, how do I find this x? You have several different ways of arriving at it. Each of these strips was 0.5 wide, so I can divide that by 2 and get 0.25, and this one will be 0.225. Another style, you can take 2 and 2.5 and average it to arrive at the midpoint. Now you go ahead and tell me, where is this point, this midpoint? What would be the coordinate? Here are the numbers you can work with. So what is that x going to be? Again, this width was 0.5, half of it is 0.25. You start at 2.5, add that, and then you get this 2.75. And this one is going to be 3.25. Let me write it outside so it's readable. 3.25, and this one is 3.75. So if I want to calculate the area using the mid rule, let's use M for mid rule. Since we have 4 rectangles here, I'm going to still say M4. The base of these rectangles, as before, is just 0.5. How tall are they? The very first one is built on 2.25, and it's going to be having a height equal to square of this, because your function was y is equal to x squared. So I take my x and square it, and that's going to give me the height of this rectangle, and multiplying it by base is going to give me the area here. Now for the next one, what was the number for this one? Let me write it here. That was 2.75. That is 2.75 squared. Next one, at this point, let me use a different color perhaps. At this midpoint, we are going straight up and making this rectangle here. So how big is that? That was here is 3.25. And finally, the last one at here, that is 3.75, and you have to square that, and then you're all done. So this becomes 0.5 times. Now I need to calculate all of these things on, let me use my calculator to find out what these things are. 2.25 squared plus 2.75 squared plus 3.25 squared plus 3.75 squared is equal to this is 37.25 apparently. Now I multiply that by 0.5, and I get I wonder if I've made a mistake, 18.625. Okay, that seems to be our answer for now. We got 18.625 here. We got different answer from trapezoid. We got here this answer 21, 22. They are kind of in the same ballpark. They are all around 20s, but they are of course too far apart from each other. What's the reason for that? Well, our approximation is quite crude. We had just 4 subintervals. How would you improve your approximation? Well, you improve your approximation by refining your subdivision, or sometimes they call it refining the mesh. Let's go ahead. To improve the accuracy, the most fundamental things that you can do is to use large N, which means large number of subdivisions or panels. So what's going to happen when you do that? You have a long summation. You have lots of rectangles. You have a long sum that you need to calculate and then plug it here. And when you do that, your numbers are going to come close to each other. These are not going to be so widely separated from each other. The numbers come close to each other. And that's going to become one of the fundamental theorems. We are not going to prove, but we are just going to state that as the number of subdivision increase, regardless of what rule you use, the end result is going to be all the same. So that's one big idea coming up. Next thing, more of an immediate concern for us is, well, what would that number be? If you subdivide and keep subdividing and getting a better and better accuracy, what would be the final limit of that process? Well, to do that, we need to be able to do certain kind of summations. You see, for example, here we are adding up several equally spaced numbers, all of them squared. For our future work, we are going to need to be able to do that to all sorts of sequence of numbers. And I'm going to mention one identity here that's going to be very useful later on. One of these identities, which you most likely know about, is the following. If I simply want to add up large number of numbers that are just separated by 1 unit apart. Suppose I want to add up numbers starting 1 all the way to some number. Suppose I want to go as far as 100. What would we get? Well, of course, you can sit down on your calculator and really just add them up. But that's going to take forever and it's going to be quite tedious. Question is, can we find a shortcut to get the answer here? Again, why are we doing this? We are preparing ourselves for lengthy summations. To make a matter easy, we are going to some nice numbers. First, we take just consecutive numbers and add them up. And we are asking ourselves, is there any easy way of doing that? Gradually, we are going to make the problem more challenging by considering all sorts of other kind of summations. But here is our very first. Suppose I want to add up all the numbers starting 1 all the way to, say, 100. The trick is, for this one, there's a simple trick, which is don't add them the way you see them, but pair them up in some other way. Pair, for example, the first and the last number and add them up. What are you going to get? Get 101. Well, go ahead and pair up the second and the one from the last. When you add them up, that also gives you 101. Now you get the idea. If you take the one just prior to that, 98, who are you going to pair it with? If you pair that with 3, you again going to get 101. 4, you pair it with 97, and so on. What's the last pair that you are going to have here? What is that? The last pair, right in the middle of here, there's a last pair. And can you tell me what are the numbers involved there? Well, of course, here we are going to end at 50, and 51 will be the last pair, and when you add them, you also get 101. Now, how many pairs do I have? Numbers from 1 through 50 have been paired with numbers from 51 through 100. So I have 50 pairs. Half as many as numbers I had at the beginning. I have 50 pairs. Each pair added up to 101. So 50 times 101 is going to be the total from here. That's just 50, 50. So what was this? 50 was half as big as the number of numbers you had. 50 is half of this. 101 is the sum of the first and last. Let me see if you can make a formula yourself. If I have 1 plus 2 plus 3 and then I go all the way to n, what is that total going to be? We apply this trick. Presumably it still applies. How many pairs am I going to have? For 100 I had 50 pairs. For n I will have n over 2 pairs. What's the subtotal of each pair? When you add the first and last, you get n plus 1. So this is one of the formulas we are going to need later on. We might as well put it in a box here. That was rather easy. After that, it's going to require substantially more work to get the identities that we want. And I'm going to just write them down right now, and perhaps in a future video we are going to show you the proof. Here is the next question. What if I square these numbers and add them up? Again, why would anybody be interested in such a thing? Just to remind you again, remember here we were squaring our numbers and adding them up, and they were equally spaced. So here we take a simplest example we can think. Here are just consecutive numbers. Every one of them is being squared. We want to add them up, and the question is, what are we going to get? The answer is not something that we can guess, and that simple trick that you saw in the previous example doesn't apply here. There are a number of ways of showing you what this is supposed to be. I just write down the answer, and perhaps I include some links for you that you can go and see a movie to show you how this magic really works. But here is n over 6 times n plus 1 times 2n plus 1. You might think that I'm just pulling this out of my sleeve, and that's because we didn't prove it. One of common objections students have is that, where did this 6 come from? I cannot really answer that. I can only turn the question back to you and say, well, where did that 2 come from? That wasn't all that justified over there either. If you shouldn't think about this as like adding fractions or taking common denominators or anything like that. This didn't come out of any fraction addition. It came out of certain other arguments. This one also has its own root, but cannot be explained all that easily right here. So let's just accept this for the moment, so that we don't get distracted into another topic that's going to keep us busy for an hour. We just put this thing here. For good measure, I also include a formula for sum of cubes of consecutive numbers. If cubes of numbers are added up all the way up to some number n, what am I going to get? The answer here turns out to be n squared over 4 times n plus 1 squared. So that's our formula number 3. Let's just go back and make sure we understand what these formulas are talking about. Let's take this one. Suppose in this formula I go as far as, say, n equal to 4. So I said in that case I'll have 1 squared, 2 squared, 3 squared, and then 4 squared, and that's where I stop. Question is, what is this total? Well, this is small enough that you can just do on your calculator quickly and find out what that is. 1 and 4 and 9 and 16. That is just 30. Is that right? Our claim is that if you want to calculate this, there is another way of doing it, which is take the very last number, that is 4, divide it by 6, take the number one after that, n plus 1, 4 plus 1 is going to be, here let me write 4 plus 1, and then double that number and add 1. Continue in another color. So this is going to be 4 over 6 times 5 times 9. Let's go ahead and simplify that one. Notice now that 6 is going to disappear. I simplify 6 and 4. This becomes 2 thirds. 9 and 3 becomes 3. 2 times 5 is 10 times 3 becomes 30. Same number. So what you get by just directly adding them up is same as what you get from this formula. Once again, you might be asking yourself, why do you torture yourself? Just go ahead and add them up. You can do the addition only if this is some fixed given number. The question is, what if you stop at some number that's given to you as some variable n? If it is n, you wouldn't be able to actually add them up the way you were doing it here. But the right hand side now has the advantage of being applicable. You just plug your n in this and you say whatever this one is, it's equal to that summation. These formulas are rather magical. They are separate topics in their own right in some courses called number theory and so on and so forth. Right now we just set them aside and we go ahead. Let's see what's the application of this. Here's a major problem. Find the exact area under y is equal to, say, x squared, and over interval, let's keep it 0 to 1. So very similar to what we did before, it's just that we are going to start from very left point of the parabola, and now let's blow this up and assume like 1 is all the way here. We want to find this exact area. How do we make our answer exact? Here is the procedure. We said to make improved estimation, you have to have lots of rectangles. So that's going to be plan of attack. We are going to set a stage for having rectangles that can be made as thin as we want them at our will. So we are going to go ahead and say, suppose we are going to divide this to lots of thin rectangles. So how many of them? And ideally we want to make these rectangles as thin as we want them. So let's take the number of rectangles let's take it to be number n. So if you decide to subdivide to 100 subintervals, n is going to be 100. If you want to subdivide to 1,000, then n is going to be 1,000. So we are letting this thing to be a variable so that later on we can play games with it and make it go to 10 and 100 and 1,000 and so on. It's going to be at our disposal. If that is n, here comes this question. How big would this base be? Suppose I tell you n is 100. Then how big is this base? So let's write it. The base of rectangle, how do you obtain it? We say that from here to here, this one is 1 minus 0, that's just 1. That's the distance from this point to this point. 0 and 1 were given to us here. Well, I take that length and divide it by as many subintervals I want. So the length of each the base of each rectangle is going to be 1 over n. So this tiny base here is 1 over n. Next, we need to choose a style of doing our approximation. You could use right, left, or middle. It makes no difference at all. To keep things simple and clean for you, I choose, we will use right endpoint rule with these n subintervals. But again, any of the rules you use will give you exact same answer. Okay. Now let's go ahead here and practice this idea of dividing 0 to n, 0 to 1 again. So I'm starting at 0, going all the way to 0.1. I'm subdividing. Where is the first subdivision? Well, it depends on what your n is. From here to here is going to be just the base of rectangle, 1 over n. Where is the next point? Well, you have to go another 1 over n. This is going to be 2 over n. Well, where is the next point? The next point is going to be 3 over n, and so on. This is going to be 4 over n. How about the very last point? The very last point, all that is exactly n over n. Who's right prior to that? Prior to that is, well, 1, subtract 1 over n from it. You could write, for example, n minus 1 over n. Did you get that? Where did that come from? Just subtract 1 over n from this. Subtract 1 over n from this, you get n minus 1 over n. If you want to go to the point prior to that, that is going to be n minus 2 over n, and so on. This business with the subdivision is something that you need to practice and become good at it, because many problems and approaches in this section requires this. Okay, what do we do after that? Let me draw the parabola again. Suppose this is a parabola. At this point, I'm supposed to go up and build my rectangle, and go up here and build that rectangle, and so on. Same as before, it's just that we shouldn't get dizzy looking at all these ends and so on. The idea is very same, just instead of 4, we are using just letter n. So let's go ahead and write the formula for Rn. You remember what we did here? We had the base. Oh, well, this is a midpoint. Let's go back up. The base, instead of half, now it's 1 over n. the first height squared, next one squared, all the way to the last one squared. So we are just going to copy same idea here. So who is the base? From here to here, the base is 1 over n. So I just write that is the base or the width. Width of all rectangles is like that. The height of very first one, x is 1 over n, squaring that would be 1 over n squared. How about the next one? Next one is x is 2 over n, that has to be squared. How about the next one? The next one is 3 over n, and that guy has to be squared. So on we go. What is the very last rectangle we built on the right side here? Well, this one. The very last rectangle we built is going to be this. How tall is it? Is 1 squared is just 1, but you'll be much better off if you write it n over n, that's just 1, squared. Then we are done. Well, we are done writing this thing. We still have long ways to go. Let's go ahead and clean this thing up. So I write again Rn, base was 1 over n. Go ahead and square all these parentheses. 1 squared over n squared. Next one is 2 squared over n squared. Next one is 3 squared over n squared. And all the numbers in between all the way to the very last one, n squared over n squared. These denominators are all the same. I can take a common denominator, which is n squared. In addition, or maybe I should better write it down. This is 1 over n. Here I take one gigantic common denominator, n squared. In numerator is 1 and 2 and 3. All of these guys squared. I might as well combine these two, n and n squared. That is n cubed. So 1 squared and 2 squared and so on, all the way to n squared. Now you see our wisdom for having worked on this 1 squared plus 2 squared plus n squared blah blah. We have a formula for it. What was the formula? Let me write it down here. You remember that was n times n plus 1 times 2n plus 1 over 6, the whole thing divided by n cubed. Let's do two things. Combine these two denominators and multiply this thing out. So I write 6n cubed. Now multiply this thing out. N times 2n is 2n squared times that makes 2n cubed. N plus 2n, please go ahead and do the multiplication. That gives you 3n times another n makes n squared. 1 times 1 times an n is going to be just like that. Since we are planning to torture you here, we go ahead and break this apart. I write it as 2n cubed over 6n cubed plus 3n squared over 6n cubed plus n over 6n cubed. I go ahead and simplify so that what I want to do with it will be easy. 2 over 6, notice that n cubed and n cubed cancel. 2 over 6 gives you just a third. Here n squared and n cubed cancel. 3 and 6 gives you 1/2, and in the denominator I just have an n left. Here all that happens is that one of the n's in the denominator is going to go. Now this is a rather neat formula. You wouldn't say it's neat, but I think it is. So what does that mean? Let's go back, see what happened. We started from this picture. We decided let's go and subdivide to n pieces. N could be any number, 5, 10, or 100, or whatever you want. We just let it be n. We went ahead, created the subdivision, found the heights, squared the heights, squared the x's and added them up, multiplied by the base, and then we went through some gymnastics here to clean it up, and out came to be this one. Now is the time to play with the n. I say if you want to make it accurate, you have to choose a very large n. So we say let n go to infinity. Choose it as large as you can. Well, what's going to happen to these guys when n goes to infinity? You remember from the beginning of the semester, or perhaps pre-calculus? That's a very simple limit theorem. Here you say limit of Rn as n goes to infinity, that is, as we are making our approximation to become exact, is going to be, I pause for a moment and you tell me what is going to be the limit of this thing. Do you have it now? The limit, of course, these guys will become negligible, and answer comes out to be 1/3. We did quite a bit of work to come to the point of finding what the area is going to be. So who is this? This is the area underneath a parabola, standard parabola of y is equal to x squared from 0 to 1. What we found out that the area is 1/3. Now you might look at all of this thing and think that, well, if calculating area is this complicated, that you are not really all that interested in finding an area. Well, let me tell you two things. One is that when you practice a few of these things, this whole process is going to be much faster, and then you go through each of them in 4 or 5 minutes, and it's not going to look like what we made it to be here. It looked a bit lengthy, but it's not really that lengthy. Second, later on at the end of this chapter or the next one, we are going to make the whole thing to happen on just half a line, and that's going to be the power of mathematics, to compress all these activities inside a very simple number of steps. And due to its importance and due to its elegance, it's going to be called the fundamental theorem of calculus, deservedly named with such a big title. Okay, maybe I stop this thing here and then continue this in part 2, so that this file wouldn't become super huge, and we put all of this stuff on more theoretical footing in the next video. So go ahead and start doing the problems of section of this chapter, and I'll post the next video pretty soon. Good luck and God bless.